Okay, students, so we're going to see on another two more algorithms on classification. This falls under the supervised learning. So one is nearest neighborhood classification, so NN. So nearest neighbor classification is actually a non-parametric and a slow learning algorithm. So it doesn't have any particular type of parameters. So it actually uses no assumptions for the underlying data. So that's why it's actually a non-parametric method. So basically from the data, when you actually find a certain kind of classifications and when you have a new data, based on the classification, you try to cluster them to the nearest neighbor. So the structure of this model is actually determined directly from the data set. So this is actually helpful in the scenarios where certain data sets that do not have any kind of assumptions on the background. For example, like linear assumptions and things like that. It learns slowly because why? It does not need any training data points for creation of the model. It uses all of the training data in the testing phase. So this is why it actually becomes slow and memory consuming. So this is the image. Like for example, the most used algorithm of this family of classifier is known as the K nearest neighborhood. Actually, nearest neighborhood NN, and usually they call it as the K nearest neighborhood, whereby the K is actually represents the number of nearest neighborhood to consider for classification. K is usually taken as a small odd numbers. It's either number of 1 or 3 or 5 and things like that. So let's say, for example, here you have an example, a 2-class problem. We want to predict the label for the test point with a question mark. That means, let's say if you have a test point here, and you want to now classify this particular test point, whether it belongs to the green star or the red triangle, which is the class A or class B. Where does this new point belong to? Where do you want to cluster it? So let's say if you take K is equals to 1, so what it will do, it will find the nearest neighborhood. K is 1 means you are considering the nearest neighbor. Only one nearest neighbor you'll consider. So in this case, when from here, compared to the triangle class B, this particular neighborhood is the closest to this point. So therefore, this question mark data point will be now classified as class A because it's closest to this. So this is how the K nearest neighborhood actually works. For any other arbitrary point value of K, we'll try to find the K closest to the test points. And then, so K not necessarily need to be 1, it can actually be more than that. But as you choose the number of K points, you'll find what is the best, that is a way of finding out what is the best K points. We will see that later point of time. And using the number of the K, he'll try to classify the test point by majority votes of his K neighbors. So let's say if you choose K is 3, and you try to see out of this 3, which 3 K neighborhood has a majority of vote to which class. So based on the majority vote, the new point will be classified as the majority vote. So this is how the K nearest neighborhood actually works. So to find the points closest or similar to the test point, we will actually use the equivalent distance. Just find the distance between points. So what are the steps to classify a test point? The first thing is you calculate the distance. You find the calculate distance means from the test point to all the nearest points. You calculate the distance and you find the closest neighbors to the test point, and then you vote for labels. Then you see out of the closest neighbors, how many of them the majority vote falls to which cluster. So based on that, the new point will be classified as the majority vote for the label. So in order for us to implement K nearest classifier in Python, so we need to import the library packages. So here we'll use the sklearn package. We want to use the data set. Here, this is one data set that we are going to actually import. This is known as the load digits. So this load digits is actually an 8x8 matrix image of handwritten digits. So that's what we are doing the first one. And the second one, we are actually going to use now the sklearn model selection library, and we are going to import what we call as the train, test, and split. So earlier we didn't define this. Now we are going to try to define the train, test, split function. And then we are going to, of course, use that sklearn. We're going to import the neighbors. This is actually under the neighbors library and then nearest neighbors library. We are going to import k neighbors. It should take note of the spelling. Classifier. K neighbors. Okay. And of course we need to get the matrix, so we're going to import the matrix. Okay, so we are actually going to, these are the things that we actually need for the libraries. So let's load the digit data set. So how do you do that? Of course, you just define a variable digits, and you're going to load it with the load digits library. So this one, if you want to see, if you print digits dot data, all the data and what's the shape of the data, you'll be able to get the output. So let me just minimize this a little bit. Yeah, so you can see this is actually the shape of the data. So it has this many rows and this many columns. And let's see if we want to plot, so they can have an idea. If we want to plot, then we need to import plotting. Yeah, we have to import the plot library, pyplot. That's the same library that we actually use. So we can set this as plt. So let's try to plot this. Plot, we're going to go use it, gray function in grayscale, and we're going to plot matrix show, and we're going to display digit images. Let's say the first image 0, and let's show the plot. See if they can see here or not. Let me minimize this. Okay, it's having error. The digit is not defined. Okay, this is digits. My bad, because here we define as digits, right? Here is digits. Okay, let's try to see. Here we have it. So you can see this is the handwritten 0. Let's see what happens if we use the first one. This is number 1. So for each number, there's a handwritten image. So number 2. Of course, it doesn't look so nice. This is the library. Okay, so this is just to show you an example of what load digits consist of. Right? Now let us actually move on to train the model using the training sets. So this is the load digits, just to visualize only. That's why we actually did this. Now let us actually train this. So when we actually want to train the model, we're going to use this particular library, train test split. So we are going to split our digits data into training and also testing. These two data sets, you're going to split them into training and also test data set. So when we look at separating them into training and testing data set, this is we need to have the x-axis and also the y-axis. Right here we have two axes, right, x and y. So you need to have Y train, Y test, X train, X test. So each corresponding with the train data set and each corresponding with the test data set. So that means we need to define 4 variables. So one is the X train, another one we need to have the X test, and then we need to have the Y train, and we need to have the Y test. So we are going to split into these 4, and we're going to use this train test split. So this will help us to split, and which data that we want to actually split? The digits. So digits, and out of the digits we need to separate the data, and also we also need to have the targets, right? So digits target variable, which is because you want to split based on the data and also the target variables. Target means the numbers matrix in order for us to train and then predict, to classify. When you actually give a new sets of matrices for each number to the model will be able to classify which number is it. And here we're going to select the test size. So we're going to set the test size as 0.25. This actually means we are doing this, right? We are splitting our data set into a ratio of 75-25. So the ratio is always comes in this format: training and test. So you just need to specify the percentage for the test set. Automatically the remaining becomes the training, right? And we are the random state, we're gonna make it 0. We don't need any random state. So next we can actually, so this is the note for earlier. We actually split our data set into a ratio this, so we use the train test split. Now we're going to actually use the KNN model for training by specifying the input and output variables of the training sets. Okay, so we are going to use the model. So let's define our model. So model, we are going to use this K neighbors classifier model, and we need to specify the number of nearest neighbors. So let's say we choose 3. Remember, it has to be an odd number selection. And now we are going to fit our model with the input values, right? The training data. So the input for the training is, of course, it has to be X train and also Y train. This has to be our training data, right? Trying to fit in our values. And now let's try to actually predict the output. We can actually try to get the confusion matrix. This is CM, and we are using the matrix library, and we are getting the confusion matrix function. So in this confusion matrix, we actually wanted to test with the Y. Y is our target, right? Y test data with the model's predicted data that is given by X test. So this is the actual Y testing data, that the target variable, and we're trying to see in terms of the output, the predicted, the Y test predicted from the model. And of course we can actually get the score. We can get model score. So this model score is based on the, of course it has to be the test data set and also the Y test. So we try to see the score with the testing data, right? So this is the output, and this section they're trying to use the plot function. So let's set the figure size. This is fig size, same as previously. We can set 9. If it's small or large, then later we can change. So for the confusion matrix, we're going to use that Seaborn. Okay, so most likely we have to import that Seaborn library. So we can just put import Seaborn as SNS. Right, we just add that. So we're going to use the heat map, and we are going to display our confusion matrix. Same as before, we're going to allow the annotation so that the proper labeling will be there. And on each segment, we want to set the float point as 3 floating point lines width. We can set as 0.5. So all these things you can actually configure it later. Square, we're going to set it square to true. We want it to be in square, and we want to set that map confusion map color using the yellow, green, and also blue combination. So we're gonna plot the label as same as before, like how we did actual label, and we're gonna plot the X label. Sorry, this is supposed to be Y label, actual label, and this must be the predicted label. Predicted label. Okay, what else is missing? Yes, we'll put that title, all sample title will set as accuracy score. And we're going to use the curly bracket 0. So this will use the format and will display the score here. And finally, we'll put in the title, plot the title, sorry. Plot the title, which is all sample title. And you're going to set the size as 15. More or less same as before. So let's see. Yeah. Okay, let us see what we actually get. Is there any error? Okay, there is some error. Okay. Here I missed the square bracket. Sorry. And now it should be fine. Sorry about that. So let's run. It's running. Let me just go out of this so you can easily see. Say some error name, all sample title. Okay, I didn't do that properly. Actual label or sample. Yeah, so this one. Now it should be fine. So this is a sample image that we actually draw just now. So here you can see the accuracy score in the confusion matrix. So it's almost close to 1. So here is the actual label for each number, right? It only has numbers 0 to 9, right? And see how it's able to predict the number. So number 2, so number 1, so number 0, it managed to actually get the confusion matrix of 37. So the darker the color, the more accurate is able to make the prediction for each one of these color. So here 0, okay, it's not so dark. It's not so dark, so it means that not all the time it able to predict or classify it correctly, but very accurately that can actually classify is number 6. So you can see this diagonal one is actually showing. So for example, you see 0, you correctly get 37 score, and see others there's no. Like for example, let's see, this is 2, 3. So you see that for example number 3, it is also mistakenly predicted as 2 wrongly, but it's just a smaller minor percentage point. So like for example 8 has been wrongly predicted with the score of 2 as 2% as number 3. So there are some wrong prediction labels are there, but most of the time it able to get a 98% accuracy score, which is quite good. Okay, so the predicted and actual labels are shown. Of course, the diagonal entries are the correct classification. So most of the time the digits are correctly classified. Some classification was there and I just showed you. Nevertheless, the model managed to show 98.67% of accuracy. So this is k-nearest neighborhood. And some of the advantage and applicability is that it's very easy to implement because you just need to specify the value of neighborhood. And of course, in a complex k-nearest neighborhood, one of the distance function is Euclidean distance. Is the simplest one. There are many others as well. So the nearest class does not learn anything in the training period. It basically is just calculates the distance. It's not optimizing anything. So this is just instance based learning. So it just uses the nearest neighborhood. The classification is done by storing the whole training data set. So this makes some of the advantages, of course, makes the nearest neighborhood classifier much faster than the logistic regression. So logistic regression needs to do the optimization. It needs to learn what is the best curve. Same with regression as well. But k-nearest neighborhood is much more easier to do the classification. Since no training is required before making predictions, new data can be added easily to the algorithm without affecting its accuracy. So this is one of its advantages. You don't need to train each and every time. Whenever you just have a new data to put in, it will consider the whole data set and it will find what's the k-nearest neighborhood and classify the new data set. So it doesn't affect its accuracy. So these are the advantages and applicability of KNN. Some of the limitation is, of course, it's very slow in the testing phase. Why? Because you need to calculate the distance of every single point. So which makes it not so suitable for very large data sets. Because why? As the point that I mentioned, you're calculating the distance from test point to each training point will definitely take a lot of time. And because it actually finds the calculation, therefore, from the test point to each training point, therefore the algorithm is very sensitive to noise and outliers. and also missing features value. So these can actually affect the classifications. So one of the way is, of course, you need to remove outliers and make sure that you impute missing values before we can apply KNN to our data set. So the next one is on the naive Bayes classification. So this is actually using the probabilistic theorem of probability. So naive Bayes is, of course, is one of the fundamental classification algorithms based on the theorem of probability. So the basic assumption used by naive Bayes classifies the independence of features. So how each features are independent of one another. So this assumption is considered naive, which actually simplifies the computation. So of course, in terms of probability, this assumption is called class conditional independence. Now, we won't be going into the theoretical aspect of how to derive the functions, nor are we actually looking into great depth of what is naive Bayes classification is all about. We're just going to understand up to this point that this is based on the theorem of probability, and we're going to use that to classify. So don't worry too much about the terms used in the naive Bayes classification. So to understand Bayes' theorem, let's try to describe the conditional probability as defined as the likelihood of occurrence of an event based on the occurrence of a previous event. Right? So let's say now we have let's define two events, event A and event B. So let's say event A, it's raining outside, and let's say it has a probability of 40% chance of raining today. So which means the probability of event A is of course 0.4. Now event B is a person needs to go outside, and just assuming the person has a probability of 30% of going outside. So this is known as event B. So when we say joint probability means it's looking at the probability that both events happen simultaneously, which is written as probability of A and B happening together. Under the conditional probability, now here is where we are actually more interested to actually know the probability of chances of occurrence of rain. Let's say the probability or the chances of occurrence of rain given the person has come out. So this how you write in probability is what is the probability. Remember the A is actually the probability of rain, and B is the condition that the person want to go out. So now what we are actually looking at the probability of occurrence of rain. So we are looking at the occurrence of rain given the condition that the person has come out. Of course, this is actually the probability mathematical formula, which is actually calculated to find the probability of rain given the person went out. So we write probability of event A given the event B have taken place. So on another note, the probability, there's another condition where related to the event, which is the probability occurrence of event B, which is the person of going out, considering that A had already occurred. So this is what is the probability of the person going out when it is already raining. So then you define it as a probability of the person going out when it is already raining. So from the formula you can see that probability of rain given that the person went out is different compared to the probability of the person going out when it's already raining. So it is not the same, it's not equal. So this is just to illustrate some point. So the conditional probability is what we actually interested for us to actually know, to find out. So let's try to implement this. So here, what we are actually going to use is we are going to set certain features and label variables. So it's already given to you, so we don't have to type it. So later we will see what are the features and what will be the label. So features, we have two features, which is the weather and also temperature. These are the features that the machine learning will take into consideration, and label variables is the target variable that we want to predict, which is the play. So basically you can see depending on the weather and also the temperature, the label variable will determine whether to play or not to play. For example, if you see the first combination, which is the weather is sunny and the temperature is hot, so it's a no. It's not a good time to go and play. The next one, sunny, hot, again no. Overcast. Overcast means there are some mild clouds. Overcast and then hot. It's actually yes. That means it's not too sunny. It's actually overcast. Means there's a cloud covering the sky. Yes. Now there is this rainy, and then there is this mild temperature, rainy. Then like still it has yes. Rainy, cold. So let me see what is this. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Yeah. Rainy, cold is no. It's not a good time to go play. So based on these inputs, now whenever you give a combination of weather and temperature, you'll give the probability of likelihood to play or not to play. So that's the understanding of the features and also the label variables. So let's try to import the Gaussian naive Bayes model. So we're going to use sklearn. So from sklearn, we're going to use naive Bayes, and we're going to import the Gaussian. So Gaussian naive Bayes is the generic one, and we are going to also import a particular library which is known as preprocessing, because we need to change all these features and label variables from string to numbers. So pre-processing. So processing. Import pre-processing. Okay. So here, suppose we want to predict whether we should play based on weather condition, temperature readings. Weather and temperature becomes our feature, and the decision to play becomes the target variable or the output. So we assign. So this is already the features and label variables are already there. So we're not going to do that. So let me make this bigger so easier for you to see. Now here's the note. Since the weather and temperature are given as strings, it's difficult to train a model based on strings. So therefore we need to transform our features and the target variable into numeric data as follows. So here is where we're going to use the label encoder. So let's define a variable as LE, label encoder. And here's where we're going to use the pre-processing library or module, and we're going to use the label encoder. So this label encoder will convert into numbers 0, 1, 2 like that. So this is the creating the label encoder, which is actually pre-processing. It uses the pre-processing library and also the label encoder modules. And now we need to convert each one of this into numbers, right? So we need to convert it. So let's see. Let's do the weather one first. So weather, we can do weather encoded. So here we're going to use the function that we have actually created, and we're going to use this fit transform module, and we need to provide the weather data. So if you want to have a look on how actually it looks like, then we can actually try to print. Let's see the weather, and this is the weather encoded. So you can see here, see how it encodes into number. So you can see 2 means what? 2 is sunny, overcast is 0, 1 is rainy. So that's how it actually does the encoding. And let's try to also encode the temperature and the play columns. So temperature encoded, the same thing that we're going to do also. So we're going to use the label encoder, and we're going to fit the transform, and we want to transform the temperature. So am I using the right one? Yes, temperature. And we are going to do the same thing for the label also. So we can just put it as label. So the label, this will be fit transform, this one will be play. So we can also print out similarly how we did for the weather. So this one we change it as temperature, this will be temperature encoded, this will be the play, and this will be label. Okay, so you can see how it encodes the weather, the temperature, and also the play. Yes, no temperature. Also have 3, 0, 1, 2, right? Because temperature we have hot, mild, and cold. So this is how we actually use and encode the strings into numbers. So now we're going to try to combine the features of weather and temperature in a single variable. So we can just create a list of tuples. So we're gonna name it as features, because features are the one that we need to provide for the training, right? So features, so we're going to use the numpy. So we need to define numpy here. Import numpy as np. So features, we're going to use the numpy. So we're going to, what we're going to do is we are going to stack all the columns together. So that is this one particular module which is known as the column stack. And we are going to, here we actually need to provide 2 columns, right? So another square bracket, because we need to define the 2, weather encoded as well as temperature encoded. So this will be our features, and let's see how it looks like when we actually print the combine. So this is how we can always view how our data looks like. Say the combined features. Combined feature, this will look as features. So let's see how the combined features look like. Yeah, say you can see how it managed to stack the weather and also temperature. Right? So now we need to generate a model using the naive Bayes classifier in the following steps. First, create a naive Bayes classifier. So just like how we did earlier, we always define the model as this is, we are using the Gaussian naive Bayes, right? We have already imported that. This is the first one. The second one is train. So this one we use the fit function. So we always need to define the features and also the label. So what is the features? We have actually combined the features already, and the label is being the target label, right? And now what is the predicted output? So we can actually get the predicted value, which is from the model predict. Now under here, the model predict, we can actually, this one will create the model and will train the model. So once you got the model, you can actually use the input to predict the outcome. So here we need to, sorry, not this square bracket. So we need to actually provide the combination. So let's say if we are choosing weather is 2 and the temperature is 0. Temperature 0 is what? Hot, hot, mild, cold. Hot, mild, cold. Sorry. Let's say if it's overcast. 0 is overcast, right, for weather. And let's say if its temperature is mild is temperature mild is 2. So this one meaning to say that we are actually trying to find out combination. 0 is actually overcast and 2 for temperature is means that the temperature is mild. So when we give this, what is the output, predicted output that you'll get, whether you'll be playing or not playing. So we can actually print out the output value. So predicted value, which is given by predicted. So what do you think? So when the sky is covered, it's not too hot, and then the temperature is mild. So what would be the predicted value? 1. So what is 1? It's actually representing the play. So that means yes, going out to play. So let's try to choose another combination, which is 2 is hot, right? 2 is hot. Sunny is weather, and we use hot is 1. So this is, let's say this is 2 and this is 1. Let's see what is the outcome. You see the outcome now becomes 0, the probability of not going out, not playing out, because 2 is actually the weather is hot, sunny, and 1 is temperature is hot. Okay, so this is actually on the naive Bayes probability. So I've already explained all this, we have already done. So let's say this is the exact step that we took just now, so I don't want to go through this. But since now we have actually classified this into numbers, encode this in numbers, you can also use the k nearest neighbors classifiers and try to find. Earlier when we actually used 0 and 2, what did we get? Yes, right. So let's see, this one coming. See why this error, the output is here. Predict. So we can actually put here the predicted value, right? It actually will show, which is actually 1. So let's say if we do the same thing, which is hot and also sunny and hot, what you'll get? Yeah, more or less the same, more or less the close answer whenever you use the k nearest classifier and also the naive Bayes. So you can actually do some benchmarking on that. So what are the advantage and applicability? Naive Bayes, of course, it's easy to implement because it's based on the probability, but then it performs better compared to other similar models, especially when the input features are independent of each other. A small amount of training is actually sufficient for this model to estimate the test data. So just now you can actually see we have very small test data, but it is actually sufficient for this model to estimate. So that's one of the advantages. But one of the limitation is, of course, the assumption that independence of the independent variables. Like for example, just now we had what is it? The weather and also the temperature, right? The assumption is these two are uh, independent. They are not dependent on one another. If they are dependent on one another, then it actually will affect on the performance of Naive Bayes. So if the features are dependent, this algorithm cannot be applied. Here also we can actually use the dimensionality reduction techniques to transform the features into a set of independent features before applying the Naive Bayes classifiers. So these are some of the things that we'll actually will see later. So, and these are the limitations that Naive Bayes have and how to overcome. Then you can actually use the dimensionality reduction techniques. So with this, we have actually covered another two more. And the next video that I'll send will be on decision tree, which will be also decision tree will be very important. So I'll stop here. Thank you.